Okay, so last lecture we had seen that we were discussing the enhancement mode Nmos transistor, and we had seen the structure of the Nmos transistor here, consisting of a p-type semiconductor with N plus source here, N plus drain here, and then we had oxide here, and on top of the metal. That's how it becomes a metal MOS structure here. And we had seen that when you apply a positive gate voltage, what it does is it pushes the holes away, creating a negatively charged region here, negative charge due to acceptor ions here. And so we call that as the depletion region. And as you create this negative charge region, as you push away the holes, we know that the product of electrons and holes is constant. So as you push away the holes, you reduce the hole density, you increase the electron density at the surface. And you increase the electron density at the surface, and thereby you create a channel, starting from source N plus here, then a channel of electrons here, and then to the drain here. And therefore, as you apply a positive gate voltage and you create these electrons here, the current starts to increase. This is the log ID versus log VG here. The current starts to increase. As you apply more gate voltage, there is more number of electrons and the current starts to increase. However, the current is very small. The channel is very weak, till you reach a point which we call as the threshold voltage here. And once you reach threshold voltage, the electron density becomes significant. In fact, at threshold, we say that the number of electrons at the surface is as large as number of holes in the p-type semiconductor here. So if the doping is 10 to the power 16, let's say here, per centimeter cube in the p-type, the number of electrons at the surface is 10 to the power 16 per centimeter cube. So we have created an inversion layer. The semiconductor was p-type, but at the surface we have created a region which is rich in electrons, and we call this as the inversion layer here. So the channel now becomes significant, and the current now also becomes significant here. And so all this happens when you exceed a voltage called VT. Alright, so on a linear plot, log ID versus log VG plot, you would see typically current would appear to be very small up to VT, and then big current begins to increase here beyond VT here on a linear plot. It gives a wrong impression that below VT the current is 0. That's why we have plotted the log ID versus log VG. Below VT there is current, but it drops sharply, exponentially with gate voltage, and becomes fairly small as you go to lower and lower gate voltages here. So we have a very important concept of threshold voltage. At threshold voltage, the channel beyond threshold voltage, the channel can be considered as strong, and the current flowing through the MOSFET is significant here. All right, so that's what we had done in the till the last lecture here. So you see depletion region, you see a channel here, and another mode, another name that we call it is inversion mode transistors. These are inversion mode transistors. Inversion mode transistors. Why? Because we've created an inversion layer at the surface. The inversion layer acts as a channel. Inversion layer acts as a channel. That's why we call this as the inversion mode MOSFET also. Alright, so that's as far as the basic operation of this particular device is concerned. So note that ID versus VG here and the concept of VT. One important point to remember is that VT is normally a constant. VT0 depends on several factors. VT0 depends on doping, depends on the nature of the metal, depends on the oxide, all kinds of things. VT0 depends. But VT0 can also be controlled by applying a body bias. So we have this expression VT equal to VT0. Gamma is a parameter multiplied by square root 2 phi f plus VBS minus square root 2 phi f. Right. Two phi f V. Let me write VSB. 2 phi f plus VSB minus 2 phi f. So VT0 is a constant. Once you choose a particular kind of a MOSFET, VT0 is fixed. Gamma is called the body parameter. It's also fixed. 2 phi f is also a fixed quantity. May vary with temperature, but is a constant. 2 phi f is called the surface potential for, but it's a constant term. And source to body voltage is something that you can apply. This is under your control, source to body voltage. So what it says is that if you apply, normally let's say the source is ground. Normally the source is ground. So what you can do is you can apply a negative voltage at the body. If you apply a negative voltage at the body, then the source to body voltage, this is a positive term. And so the whole thing is positive, and you can make VT larger than VT0. VT can be made larger than VT0 if VSB is greater than 0. So if you make the body voltage negative, then you can increase the threshold voltage. So you may be given a threshold voltage of, let's say, 1 volt, but once you're given this parameter, by applying a suitable voltage here, you could get VT equal to 1.5. You could increase it by applying a suitable source to body voltage here. So sometimes this is utilized, body of the MOSFET is utilized to apply a voltage in order to change the VT. Now you can apply positive voltage at the body also. Positive voltage at the body also, but there's a problem with positive voltage because there's a PN junction here, between here and here that you see here. There's a PN junction. If you apply positive voltage, the PN junction will get forward biased. And PN junction will get forward biased, and you will start getting a current between body and source, which is not wanted. So normally we don't apply, if we apply a positive voltage, we apply very low positive voltage, 0.2, 0.3 or so. We don't apply a high positive voltage because a leakage, a current forward biasing of the diode will occur, and that's something that we normally don't want. We don't want current to be flowing between the body and the source. A MOSFET is designed in such a way that the current flows between source and drain, and no current should flow between the body and the source. So normally we do not forward bias the body here with respect to the source here. Body may be reverse bias in order to make this here. So you have to watch out whenever you use a MOSFET, you have to watch out that the body source junction or body drain junction does not get forward biased. You don't want current flowing from between the body and the source and body and the drain here. So you have to watch out for that in the circuits. You have to ensure that the body source junction is reverse biased. Alright, so that's the basic operation here. So we from this discussion we know that Vt is an important parameter which marks the what does Vt represent? It marks the creation of a strong channel. Beyond Vt you get a reasonably strong channel here, and the current starts increasing, becomes significant with Vg here. Below Vt the current falls exponentially here. There's an exponential region here, okay? Above, we will give you a model in a minute. So that's with respect to the gate voltage. The next thing is, what happens if you say MOSFET here? Let's put this to ground. Let's put this to ground here, and let's create a oxide here, and let's create the metal. Vg here. Let's say we have applied Vg greater than Vt. For the sake of argument, let's say Vt0 is 1 volt, right? And we have applied Vg greater than Vt0, so we have applied Vg equal to, say, 2 volt. Say 2 volt, okay? This is ground and Vt0 is equal to 2 volt. So we have applied, so which means that, and for the moment, let's say this is also ground, drain is also ground. So which means that inside the device, what I have is a depletion region here, a depletion region, and at the surface I have electrons, a channel, inversion layer. All these electrons are there. The channel exists. The channel exists. As I said, we also call this as the inversion charge. This we call as the inversion charge here. Q inversion. The channel is also called Q inversion, inversion charge. And the inversion charge we write as Cox prime, which is the capacitance here. Note that there is a parallel plate capacitance here between the metal here and the inversion charge. So Cox prime multiplied by VGS minus VT. That's how we understand the inversion charge. Cox prime is nothing but epsilon oxide, this is the oxide, this thing, divided by the thickness of the oxide here. So it's nothing but, you know, from your parallel plate capacitor, you know that Q equal to CV, the amount of charge Q equal to CV. Well, in this case, the charge that we are talking about is the inversion charge. Inversion charge is also C into V, except that inversion charge, significant inversion charge occurs only when voltage is greater than Vt. Below Vt, the inversion charge is small. So that's why this VGS minus Vt is there. So it's nothing but the expression for parallel plate capacitor. So that's the amount of inversion charge that is there. You can calculate. If somebody tells you Vt0, so since we have not applied any source to body voltage, so according to our model, VSB is equal to 0, so Vt is also equal to Vt0. Vt is also equal to Vt0, which is 1 volt. So we can calculate how much is the inversion charge right throughout, okay? So that's when you apply 0 volt. But suppose now I apply a voltage here, say 0.5 volt. We apply a voltage 0.5 volt. Now, still the parallel plate capacitance equation is valid. This equation is valid. But note that the voltage, when you apply 0.5 volt here, the voltage in the channel here is 0.5. Here the voltage is 0.5. Here, somewhere here, the voltage may be 0.4. Here, somewhere here, the voltage may be 0.3. Here, somewhere the voltage may be 0.1. Here, very close, this is close to the source, so the voltage here would be 0. So the voltage in the channel is varying now. At one end you have 0.5 volt because you've applied 0.5 volt here. Somewhere you have 0.4, somewhere you have 0.3, somewhere you have 0.1, somewhere you have 0. So the inversion charge is now goes as Q inversion equal to Cox prime. This equation modifies into VGS minus VT minus V channel, because the parallel plate capacitor is here. The voltage across the parallel plate capacitor here is different. 2 volt is here, but the channel voltage is something else. So the voltage across this is something else, is VGS minus the channel voltage here. And the parallel plate capacitor here, the voltage across it is different. So because of the difference, channel voltage here, channel voltage is 0.5 here and 0 here, the Q inversion charge is given by Cox VGS minus VT minus V channel. So the amount of inversion charge is decreasing. If I were to plot the inversion charge, Q inversion versus X here, let's say this X equal to 0 denotes the starting point and X equal to L denotes the drain end. So inversion charge in some form, maximum here and will be decreasing here like this towards the end. Maximum inversion charge here and minimum inversion charge here. So in some way, we are drawing only the qualitative, so inversion charge is decreasing. Okay. So now when you apply this 0.5 volt, so the way to think about a MOSFET is that this inversion layer acts like a resistor, and you apply a 0.5 volt, and so there's a voltage across the resistor and the current starts to flow. So if I look at the characteristics, ID, drain current versus VDS, the characteristics looks like this here. ID versus VDS. For a fixed VGS, VGS is constant. For a VGS is constant. Now there are interesting things here. The first one is that when you apply a very low voltage here, at this point, we apply, let's say, instead of 0.5, suppose I apply 0.02 volt here, very small voltage here, 0.02, the voltage is at 0. Remember, what is the effective, yes, the channel voltage is different, but V channel will be so small. V channel is so small because V channel will vary from 0.02 here to 0 here. It's so small compared to VGS. VGS is 2, VT is 1, and so 1 minus 0.02, it doesn't make any difference. So Q inversion is the same everywhere. It acts like a resistor, and the current voltage characteristics is linear. Right? It starts off as linear characteristics. But then as you make it higher, say 0.2, now what happens is the channel voltage is changing. And the inversion charge, as you can see here. So let me draw the inversion charge. At very small bias, the inversion charge would be like this, constant everywhere for very small bias. If I increase the bias a little bit, the inversion charge may go like this here. It decreases. This point is fixed. The inversion charge is fixed here because gate voltage is fixed. The channel voltage is also fixed. Right? And at this end it starts decreasing. So the inversion charge becomes a little less here. And as the inversion charge becomes less, the consequence of this is that the resistance goes up. Less charge means resistance goes up. And that's why you see that the graph starts bending. Higher resistance means the slope is decreasing, which means that the resistance is increasing. You apply even higher bias, then it goes like this. Inversion charge goes like this here. It bends even more. The current is no longer increasing linearly, it bends even more. Eventually you realize that if you apply a voltage here, which is let's say 1 volt here. If you apply 1 volt here, why 1 volt? Note that this is 2, this is 1, and at this end the V channel is equal to 1 volt. So 2 minus 1 minus 1, inversion charge goes to 0. So you reach a case where eventually inversion charge almost goes to 0 here. This is the point where the current begins to saturate. The current begins to saturate here. All right, where your inversion charge goes to 0 here. So we say saturation has occurred in the MOSFET here. I'll not go into the details. So this is the point where, this is the point which we call as the pinch-off point. Pinch-off point, because inversion charge almost goes to 0. Things are more complicated. It doesn't actually go to 0. There's a high field region and all that you'll study later on in the course. But the point is that as you keep on applying higher and higher drain bias, the amount of inversion charge keeps on decreasing. So this is at VDS equal to 0. This may be VDS equal to, say, 0.2 volt, and like that, keep on increasing. VDS is increasing here, and eventually the pinch-off occurs here. So when the pinch-off occurs, the current saturates. The current no longer increases here. The current saturates. So the saturation voltage, the voltage at which the current saturates, we call it as VD sat. It's nothing but equal to VGS minus VT. It's an important equation, VD sat here. VDS equal to VGS minus VT. Why? Because this is the voltage at which inversion charge goes to 0 here. This is VGS minus VT. So you apply a voltage VDS here equal to VGS minus VT. The inversion charge goes to 0 here. Pinch off occurs here and saturation occurs in the characteristics. Okay, so what we have is a situation. Let me draw the characteristics. We have this MOSFET that you see here. Drain, source, gate, body. MOSFET that you see here is characteristics. So the only characteristics are, if we draw IDS, current flows between drain and source, current flows like this, versus VDS. Characteristics go like this here. I'm not drawing, it starts off linear, no, plus goes like this here. This is the point where it flattens off, which we call, there's an important point which we call as VD sat. And this is equal to VGS minus VT. So all this region is called saturation region. This region is called saturation region here, this one. Unlike bipolar transistor. Alright, so this region is called saturation region. And this region, it goes by the name, is called the linear region. It's not exactly linear. It's called the linear region. Why? Only the region here is linear. It starts off as linear, but then it starts to curve here. Note that starts to bend and eventually becomes constant here. So this is called the linear region, this is called the saturation region. And all this is true when you apply a gate to source voltage which is larger than threshold voltage. We have to create a channel first. And then the ID versus VDS goes like this here. So what we need to do is we need to understand the equation now. So equation is for the linear region. For the linear region here. Linear region is this first region, region 1. This is region 2. Linear region is region 1. So in this case, the current goes as the following. IDS is equal to W by L here, mu, mobility, Cox prime, VGS minus VT, VDS minus VDS square by 2. That's how it goes here. W is the width of the MOSFET. W is the width of the MOSFET. width of the device, L the length, mu mobility of the carriers, electrons, C oxide prime is the capacitance, oxide capacitance per unit area, we already said is equal to E ox by T oxide here. Threshold voltage we've already defined, Vt, and Vds is the applied voltage here. Alright, so all the terms are here, and you can see that if Vds is small, for Vds which is small, you can see that IDS, if Vds is small, then this term, quadratic term, is negligible, and you could say IDS equal to W by L mu C oxide prime VGS minus VT multiplied by VDS. That's why this region gets the name linear region here. Note that it goes linearly with VDS here for small VDS. Okay, so that's how the current goes in the linear mode of operation. Yeah, sometimes one doesn't talk about mu and Cox. One defines a new parameter called Kpn, which is equal to mu times C oxide prime. So sometimes mobility and Cox is not given. What is given to you is the value of Kpn. Okay, so W by L, this is Kpn, VGS minus VT, VDS minus VDS squared by 2. So that's the linear region of operation. In the saturation region, IDS goes as, so in saturation, IDS you can see is almost independent. IDS is W by L Kpn VGS minus VT square by 2. It's almost independent of VDS, but if you look at it closely, there is a small slope, so we multiplied by, to be more accurate, is equal to 1 plus lambda n VDS here. So that's the model in saturation. IDS is W by L Kpn VGS minus VT square by 2, 1 plus lambda n VDS here. Lambda n is like the early voltage here, except that is called the channel length modulation parameter. Channel length modulation parameter. Channel length modulation parameter. So this is giving you the model in both linear as well as saturation region. How current goes in linear region, how current goes in saturation region. Okay. All right, so that you understand this a little better, let me give you some examples. Let's say you have a MOSFET. You have a MOSFET here, and let's give you the values. So this is ground, this is 2 volt, and this is 0.2 volt. All right, now I want you to calculate the current ID equal to, how much is it? Now to do that calculation, first of all I have to know the parameters of this particular MOSFET, and two parameters I'm giving you: VT0 equal to 1 volt, Kpn equal to say 100 microamperes per volt, per volt square, kPn. You need to know, in a MOSFET, you need to know the size of the MOSFET. Size of the MOSFET we indicate here. Next to the MOSFET we indicate 10 by 1. When we write like this 10 by 1, it means W is, say, 10 micron and L equal to 1 micron. Okay, 10 by 1. Or even if it's not, let's say you want to write in this 10 by 1 basically means W by L equal to 10. That's what it is. So you know VT0, you know kPn, and all the bias values are given, and you have to calculate what is ID. So the first thing that you do in all of this is, before you start, you calculate what is VGS. That's the first thing, step number 1. What is VGS? So calculate VGS, 2 minus 0. So VGS is 2 minus 0. That's the first thing. Now, check VGS. Is VGS greater than VT? The answer is yes. VGS is greater than VT. So the MOSFET is operating in strong inversion condition. Okay? MOSFET is, so basically MOSFET is acting in above threshold. So that's important. Before using the equation, I have to be sure that MOSFET is above threshold, right? That's what it implies. The next thing that I have to know is MOS in linear or saturation region? Because we have two different equations in linear and saturation. Alright, here another parameter that I can give you is lambda n. Lambda n is, let's say, 0.01 volt inverse. So VT0 we have given you, kPn we have given you, lambda n we have given you, size is given here. So is MOS in linear or saturation region? For that, what you should do is you should calculate VD sat. VD sat is VGS minus VT. So that's equal to 2 minus VT is 1, so this is equal to 1 volt. And we find that VDS is less than VD sat. VDS is less than VD sat, so it means that my, remember that MOSFET characteristics is like this, and this point is VD sat. This is VDS, and this is ID. So VDS is less than VD sat implies linear region. Once you know it is linear region, then write down the equation for linear region. Remember, you have to remember the equation for the linear region. IDS is W by L, Kp is given, kPn, all the quantities are given, VGS minus VT, VDS minus VDS square by 2. So all that you need to do is plug in all the values here, everything is given, and you get your answer. So you calculate how much is the current flowing through the MOSFET. Okay. Same problem, similar, I could change it to by writing here how much if I apply 3 volt here. So if I apply 3 volt here, you would immediately see VDS is not less than VD sat. So the transistor is in saturation region, and you would then write down a separate equation. Then you would write down, in that case, transistor is in saturation, you would write W by L, kPn, VGS minus VT square by 2 into 1 plus lambda and VDS. 1 plus lambda and VDS. So you would use this equation to calculate the current here. All right. Or if somebody could change the problem and say, well, this is equal to 0.7 volt. If it is 0.7 volt, VGS is not more than VT. VGS is less than VT. Now, when you say 0.7 volt, VGS is less than VT. VGS is less than VT, so it's actually working in subthreshold region. Subthreshold region. And we have not given you the model, but in subthreshold region, the current, we said, when you plot, the current goes like this, exponential, ln ID. It's not so important for us, the current drops exponential. So if we give you an expression for this exponential characteristics, then you'll be able to calculate how the current goes here in this particular region here. So in the subthreshold region here, below VT. Okay, so you may sometimes operate MOSFET below VT, where the characteristics of the MOSFET ID is proportional to e to the power QVG by some eta KT. You know, the relationship starts to resemble like a bipolar. Current is proportional to, exponentially proportional to the base current. In this case, current goes exponentially with gate to source voltage. All right, so this is how you end up calculating the characteristics which are there for your MOSFET here in saturation region. So, so how should you think of a MOSFET? As I said many times, we'll just draw like this here, MOSFET here. So you should think of a MOSFET that between gate, source, and drain, a body is short. When we draw like this, body is shorted to source. Body is shorted. Body is shorted to source here. Body is shorted to source, implying that VSB equal to 0, implying that VT equal to VT0, right? So in this case, you should think of that if I have gate here, I have source here, and I have drain here. Drain, source, and gate. So I should think of that between gate and source I have nothing, DC model. Between gate and source, nothing, no current is flowing. Between drain and source, I have a current source, I have a voltage dependent current source here. IDS. This is the IDS here. And we have expression for IDS. We have given you expressions for IDS. IDS, which is a function of VGS. So it's a voltage dependent current source. Voltage dependent current source. And our interest is mostly in analog circuits where these transistors are primarily used in saturation region. We said saturation region is the constant region here, IDS versus VGS here. We would like to use it in this region here, saturation, where IDS versus VGS we've already seen. IDS goes as KPN W by L VGS minus VT square by 2 into 1 plus lambda VDS here. So it is weakly dependent on drain to source voltage. So in most of the DC analysis, we consider this factor as 1, and we take this. The first term is what we take here. This part is what we take here as the current in saturation, because the other term is not too large. So that's the model of the transistor that we have in linear and in saturation region.
So that intersect on the x-axis will be VGS or VDS?
Which one?
IDS versus
VDS. This is VDS. IDS versus VDS. IDS versus VDS. Okay, so let's look at a circuit then. For example, let me draw a circuit and let's see similar circuit. Say we have here we have here, and we put here, say 3 volt. We put here, let's say here, right, let's say we put here R1, R2, and we put here RD, right? And the values are given. The values are KPN is 100 microamperes per volt square, VT0 is equal to 1 volt, lambda n equal to 0.01 volt inverse. All these values are given. Okay. Now I want to determine R1 and R2. Find R1, R2 such that IDS equal to find also in many of these designs you have to, this W by L in most of these designs, W by L is under designer's control. Under designer's control. Actually, what happens is when you choose a particular technology, L is fixed, sort of L minimum is fixed. L minimum is fixed. You know, people talk about a 1 micron MOS technology, or you will hear 90 nanometer MOS technology. You will hear of these words: 90 nanometer, 1 micron, 45 nanometer MOS technology, 22 nanometer MOS technology. Different kinds of technologies are available. What this 22 and 45, it refers to the L minimum that is possible in this technology. So what it says, if I'm using a 1 micron MOS technology, the minimum L that I can use is 1 micron. Minimum L is 1 micron. W, I can choose anything above 1 micron. W could be anything above 1 micron. So the designer could choose W equal to 1 micron. He could choose 2 micron, 3 micron, 4 micron, whatever. W could be anything greater than this. But L, you are limited to L minimum. Of course, you can make L larger also. You can make L 2 micron. But normally, we want to keep the area of the transistor minimum. Area of the transistor is what? Area will be related to L into W, will be proportional maybe to L into W. So while my current, if you look at the expression for current only depends on W by L. So if you need a W by L of, let's say, 10, to keep the area minimum, what I would like to do is, if I require W by L of 10, I will use L, which is L minimum, that is allowed by a technology, and W then I will use L minimum multiplied by 10. Right? So that's how most of the designs are done. Most of the MOSFET designs are for a particular technology, 80 nanometer, 90 nanometer, 45 nanometer, or whatever it is. Okay? So L minimum is fixed. And most of the time, as I've been saying, you choose L minimum. To keep your area, this thing, you choose L minimum. And the W, then you can choose appropriately according to your design. So as a designer, what is under your control is, of course, you can choose R1 and R2 and RD. You can decide what to do, what to put these values here. You also have W by L under your control. You can decide you want W by L equal to 10, 20, 30, whatever you want. You can put that there. Of course, you can't use very unrealistic values, but you know, W by L of 100 also people use, W by L of 200, 300, all these values are possible here. So that's an additional thing that is there under your control here. So right now, let me make the problem a little simpler by saying W by L is given to you. W by L is equal to 10. Okay. So find R1, R2 such that IDS equal to, say, IDS equal to, say, 50 microamperes. Okay. I want to bias it at 50 microamperes. So how do I do that? How do I find and let's say for our for discussion, let's suppose we are using a older technology. Let's say we are using a say we are using a 180 nanometer technology. It doesn't matter, but let's say we are using 180 nanometer of technology. So anyway, so L minimum will be 180. You will use L equal to 180, and W you will use equal to 1800 nanometer. Okay. So how do I find the R1, R2? How do I find that out? Now note that I want IDS equal to 50 microamperes, and let's say, and VDS equal to 1.5 volt. Let's put that. So bias point would be a value of current and a value of VDS. RD is not given. You have to choose RD. So RD is straightforward. This is 3, and VDS is given as 1.5. So 3 minus 1.5, current is 50 microamperes. So you can just calculate. RD is straightforward. So RD is RD is 3 minus 1.5 by 50 microamperes. So that gives you 1.5 by 50. Right? So you can get your answer. RD is okay. How do I find the R1 and R2? How do I find R1 and R2? Well, remember what we are saying is that the transistor has to be in saturation. We are saying bias it in saturation region. We want to use it as an amplifier. Right? So in saturation region, then what we do is we use the equation for saturation region. We use the equation for saturation, and then you have to become familiar. IDS is W by L Kp VGS minus VT square by 2. So this equation tells us that VGS, the voltage that I require at this point, VGS is equal to square root 2 IDS Kpn W by L, right, plus VT. Square root 2 IDS Kpn W by L plus VT. So that's the value of VGS that I require. Many times, people call Kpn W by L, they multiply together, and they call this beta N. The Kpn multiplied by W by L is given a name called beta N. It has the same units as a Kpn, but instead of writing Kpn W by L and all that, just simply writing beta N. So this equation could have been written as square root 2ID by beta N plus VT. So how much does this come out to be? Let's see. 2ID by beta N. ID is 50 microamperes, so 2ID is 100 microamperes. 100 microamperes divided by Kpn is 100 microamperes, W by L is 10. W by L is 10, so it's basically the first term I think turns out to be 0.3, and VT is 1. So what we need to do is apply a VGS equal to 1.3 volt roughly. I need to apply a VGS of 1.3 volt. At this point you can check VGS is 1.3 volt and VDS is given as 1.5, so this is okay. VDS is greater than VGS minus VT. So the transistor is in saturation region. Okay? Transistor is in saturation region. Alright, so this is there. So VGS is this, and we can check out that VDS equal to 1.5 is greater than VGS minus VT. So transistor is in saturation. So that's not a problem. In our design, if I apply VGS equal to 1.3, transistor would be in saturation region, so that's okay. The next thing is, how do I figure out R1 and R2? Now note that R1 and R2, in a MOSFET, the gate current is 0 because it's oxide. So it's a pure voltage divider. It's a pure voltage divider. So which means that all that I need to do is this 3 volt multiplied by R2 by R1 plus R2 equal to 1.3 volt. 1.3 volt. Right, so this is equal to 1.3 volt here. And this one, basically from here, what you will be able to get is this ratio R2 by R1. You will get this ratio. It will give you the ratio R2 by R1 or R1 by R2, whatever. You'll get a ratio here. So it doesn't give you the value of R1 and R2. Now you could choose at this point, the problem doesn't have enough information. So you could choose R1 some value, some high value maybe, if it depends on, because eventually if you make an amplifier, you may construct something here and you may want a higher input resistance or something. So say if you choose R1 equal to say 100K, then R2 you will get the value. Whatever R2 you want, you will get the particular value. Okay, so by this means one can bias the circuit at a certain value of IDS and certain value of VDS. Except that there's a little bit of a problem. Let me go back to that circuit that I've drawn. This MOSFET circuit here. I've drawn this circuit here. And we said this, we are using this for biasing. R1, R2, RD, and we're using this for biasing. This will be some VDD here. And so R1 and R2 basically, as we just discussed, R1 and R2 will decide this value VG. Source is ground, will decide this value VG, and the current is ID equal to beta N VGS minus VT square by 2. Right, so that's the idea, that use the ratio R1 and R2 to fix the value of VG here. That decides the VGS here. VT is fixed. Beta N is let's say W by L is given to you, so beta N is fixed here, and that decides the value of ID. That decides the value of ID. Okay, there's a problem here. If VT, again, just like VT may vary from device to device, beta N may also vary from one MOSFET to the next MOSFET here. So what would happen is that even though you've in all cases you choose R1, R2, which is the same, you may end up getting different currents. Why? Because of variation in VT beta will cause variations in basically ID. And if ID vary, then VDS also will vary. So the bias point will vary here. So that's the problem. Any variation in VT and beta will cause directly variation in current. So just like we wanted a beta insensitive circuit here, we also want a circuit which is less sensitive to variations in VT and this here. All right. So with that in mind, what we do is we make this circuit. What we do is we modify this here and we put a resistor here, RS. We put this resistor RS here. So putting this resistor RS, now the equation, note that the equation becomes, if I rewrite it, ID beta N, same, the transistor is still in saturation. This voltage is fixed, let's call this the gate voltage VG, but VGS becomes VG minus ID RS. Note that this is VS. This is Vs, the voltage, source voltages, whatever current ID flows multiplied by Rs. So this is Vs. So VGS is Vg minus ID Rs minus Vt square. Now the current becomes like this here. Okay? Let me erase this, okay, so that you're not confused. So here. So now the current goes like this. So it's a quadratic equation that we need to solve in order to get the value of the, if Rs is given to you, so it's a quadratic equation that you need to solve to get the value of the current. But how is this biasing better? Well, the reason is, if you look at if you compare this expression with the previous expression, compare this one versus this, compare the two. In this case, if let's say Vt varies, suppose Vt increases for some reason. If Vt increases, well, the current would fall. Vt increases, the current would fall. If the current earlier was, let's say, 50 microamperes, the current may fall to 40 microamperes. Right? Immediately there would be an effect on ID. Compare that here. Compare that here if Vt increases. If Vt increases, look at what is happening. Look at the effect. In the first case, case 1, Vt increases, immediately causes ID to fall. That's the behavior. In the next case, well, Vt increases. Increase in Vt, what will it tend to do to ID? Causes it to fall, tendency. But note that if ID falls, what happens to this term? This term falls. Vs. What is this term? Vs. This term falls. What is the effect of this fall in Vs? What will it tend to do? What will it tend to do ID? Increase ID. Are you saying that there is a negative feedback loop here? Is counteracting the effect of Vt. A change in Vt would tend to cause decrease in current, but decrease in current would cause this Vs to decrease, and Vs to decrease has an effect of increasing ID. So a negative feedback loop is here. A negative feedback loop has been put. And as a result of this negative feedback loop, what you find is effect of delta Vt, any change in Vt is minimized. That's why you put this Rs there, to minimize the effect of this thing. Same thing it happens with beta n. Here, a increase in beta n, say increase in beta n, would immediately cause ID to increase. Well, here also an increase in beta n would cause ID to increase, but as ID increases, Vs also, this drop increases, and therefore it has an effect of reducing ID. So there is a negative feedback loop which has been put, which is trying to minimize the effects of these variations. So that's why we put this RS there. Often in the biasing we put this RS term there to include in biasing. So given some value of R1, given some value of R2, given some value of RS, well, this is the equation that you need to solve. ID equal to beta n by 2 Vg minus ID Rs minus Vt squared. So if you know Vt, you know Vg, you know RS, you know beta n, you know all of these things here, beta n, all of that. So it's a quadratic equation that you need to solve to get the value of current flow. Okay, so it's a little bit more complex. It's a quadratic equation that you need to solve to get the current here. Okay. So that's how you solve the DC circuits. So all this is DC circuits. DC circuits. So all you have to know, DC circuits where transistor is biased in saturation region. This is the expression for current. VGS minus VT squared. Beta n VGS minus VT squared by 2. The next thing is the small signal. Small signal model. Well, in the small signal model, let me remind you, in a bipolar transistor, the DC model was like this. There was a diode here, there was this current equation here, and this DC this is the DC model here, and from there the small signal model became R pi, and it became here GM V pi, and it became R0 like this here. This was emitter, this was base, and this was collector. In our case, for a MOSFET, well, MOSFET, let's say a MOSFET like this here, we'll take body and source to be shorted together. If you don't want body and source to be shorted together, it's also okay. We will see later on. So in this case, the MOSFET looks like this here. This is source. There's nothing between source. This is gate. Gate here. This is source here, and this is the current source here, and this is the here. Remember the current source here? The current source I was I equal to I basically equal to beta IB multiplied by 1 plus VCE by VA. Or the other and IB, note that IB was equal to some saturation current e to the power VBE by VT here. Right. So basically IC is some function of VBE and some function of VCE, and then it becomes like this here. So in this case also you have ID. ID is some function of VGS, and so ID is nothing but ID is beta n VGS minus VT. We have been saying square by 2, 1 plus lambda VDS here. So on the small signal, what happens is this then becomes like this here. Square root, gate. There's nothing in between. Nothing in between gate and source. Between drain and source, what happens is we put a current source, same current source here like GM, but instead of calling, we call this voltage VGS, small signal VGS, so GM VGS, and we put R0, same R0. So this is the gate, this is drain, and this is source. So same GM is GM VGS and R0 here, and very similar expressions. R0, so let me, we will not derive it. R0 is given by 1 over lambda n by IDS. That's easy. R0 is given by this. And GM we can show is square root 2 IDS multiplied by beta n. All this is in saturation region. All this is in saturation region. So once I know the bias point, then I can calculate GM. GM is 2 IDS times beta, and I can calculate R0. And we have the small signal model of a MOSFET which is ready here. Now sometimes what happens is that the body is not shorted to source. Body is not shorted to source. That is, we have here, and you know, source is separate, drain is separate, gate is separate, and body is separate here. In that case, there could be a voltage between body and source. So in that case, the model becomes like this here. Let me draw here. So this is source. This is source terminal. This is gate here. This is drain here. And we've already seen that this GM VGS is there. And we've already seen that this is R0 there. But then we have one more terminal which is available, which is the body terminal, because body may not be ground, source may not be ground, there may be a voltage here. So this body terminal here, the way it affects, if you recall, current is ID equal to beta n. We have been saying current is like VGS minus VT squared by 2, 1 plus lambda n VDS. Now note that the dependence on VGS, ID is dependent on VGS. This causes this current source to come. Because ID is dependent on VGS, so any change in ID would be related to a change in VGS. So we call this GM delta VGS. Right? So this is why ID equal to GM VGS. That's the source of this particular term here. That's the source of this particular term here. You also know from this expression that delta ID would also depend on delta VDS. And that's the source of this particular term here. Right? So if you look at ID, then any change in ID is due to a change in VGS, due to a change in VDS here. That's what is coming. But you also note from here that delta ID would also be related to a change in VT, and change in VT caused by a change in source to body voltage. So we denote that by saying GMB delta VSP. Alright, so that allows us to write another current source here. Everything's a reference to source. So remember what, so we write this as GMB VBS. Yeah. So one more current source. So remember what this ID is. ID refers to the small signal. ID is, we said small signal means it is a change in current. Change in current. Change in current can come about because of change in VGS, can come about due to change in VDS, and can come about due to change in VBS. These three things here. Each change is represented by a term. GMVGS, GMVBVS, and R0. Alright, so that's a more complete model for a MOSFET here. There's another current source, GM, and depends on VBS. But as I said, most of the time we may make a circuit where the source and body voltage may be short. And so therefore, this term may not come into picture. GM VBS may not come because source and body are short here. But one needs to be aware of In many places it is required also. But this is also something that we will call as low frequency small signal model, because we have not added capacitances here. We have not added the capacitances between the two parts here. So let's add the capacitance here. Let's make the complete small signal model here. Complete small signal model. Right, so again let's draw. This is my source side, this is my gate, this is my drain here, this is my body here. We put all these. Now by now you should know these terms here. 2 current sources and 1 R0. Right, so we have seen this here. So this much we have seen. Now where are the capacitances? Let me draw the first of all the MOSFET here so that you see the capacitances. N plus, N plus, here. Two capacitances are very easy to see. Source, drain. Between, this is body. Between source and body, note that there is a PN junction here. There's a diode here. And every diode has a junction capacitance. So between source and body, put a capacitance here. We call this capacitance CSB, between source and body. Between drain and body also these are all reverse bias capacitance. There's also a diode here. So we call this capacitance here between drain and body CDB. CDB and CSB. Two capacitances which are obvious. Then note that, keep in mind, capacitance is what? Del Q by del V. Capacitance is del Q by del V. We know that there is an inversion charge here. There's an inversion charge here. As you change the gate voltage, VG, as you change the gate voltage, if VG increases, the inversion charge increases. If VG decreases, the inversion charge decreases. So there's a capacitance. There's a capacitance between gate and source. The inversion charge, where does it come from? From the source here. So there's a capacitance between the gate and source here, CGS. And similarly, some of this inversion charge may come from the drain also. So there's a capacitance here between the gate and drain here, CGD here. So you see source to body voltage, you see drain to body voltage, drain to body capacitance, you see CGS, you see CGD. The CGS and CGD also come because note that there's an overlap region here. There's an overlap between the gate. Apart from the inversion layer, there's an overlap capacitance between, there's a gate here, there's a silicon dioxide here, and there is an N plus here. So there's an overlap here. Similarly, there's an overlap here between the gate. So it's called gate source overlap. Gate source overlap. So in this CGS, when I've drawn, there is an overlap capacitance, then there is due to inversion layer, all that is there. And between CGD and again is because of that. Okay. So those are the 4 major capacitances. It's not easy to see. There may be a capacitance between gate and body also. And sometimes people include that also. There's a gate and body capacitance also. CGB. Okay, so finally what one needs is how do we calculate these things? How do we calculate these things? So CSB normally is the way it goes is it's like a diode capacitance. So maybe there is some CJ0, zero bias capacitance, divided by 1 minus VSB, VBS, by some built-in voltage, some factor M here, similar to that, multiplied by the area of this source and body. Area term has to be the area source body area here. So it's like a PN junction capacitance. Drain to body is also like that. Drain to body is also CJ0, 1 minus VBD by VBI to the power M. Area, drain area. Depends on how large is this area here. Similarly, depends on the source area here. So let me write it source area here. Because this entire source region here, whatever is the area of this region, will give rise to this PN junction is all over. Here, everywhere. Similarly, PN junction is all over. So it depends on the area of the drain. Area of the drain, area of the source. That decides CSB and CDB. And of course the bias. As I said, normally body would be negative with respect to source, so this term is positive, and body and drain are anyway negative. VBD is negative. So this capacitance here. So it's a PN junction capacitance. The CGS that you see here, so we are talking about saturation region. So CGS, in one case we write it as 2/3 C oxide prime W into L. That's one term. We have given you what is this is the oxide capacitance per unit area, this is the width of the device, this is the length, and 2/3 is because it's non-uniform charge, so 2/3 comes in. Plus it has another term which we call as CGS0 overlap multiplied by W. So it has two terms in it. There is a term due to the channel and there is a term due to overlap here. CGD on the other hand, most of the time we model it like this, CGD 0 times W here, overlap capacitance only. Alright, so these four, and CGB here, this is usually very small. Small, most of the time we don't take that into account. Anyway, to use the full high frequency model, we need to then find CGS, CGD, CSB, CDB. Now most of the time, as I said, you may find that source and body are shorted together. So this capacitance then gets shorted. But CDB is very important, CGS is very important, and CGD is very important. Three very, very important capacitances without which you cannot do any high frequency analysis. To calculate the drain to body capacitance, I have to know what is the body to drain voltage here. I have to know the model CJ0 and M and all that, and I have to know the area of the drain. How big is this drain area here? This drain area, what is the length, the area of that particular region? Okay, so we have the DC model and we have the small signal model. So now we are in a position to do all that we did with BGT amplifiers here. So you could, for example, start with, let's say, a common source amplifier. We could construct a common source amplifier using an Nmos like this. So body and source are shorted together. We would put an RS here, and we would put here, and we'll put a resistor here, VDD, RD here, we'll put a R1 here, R1 and R2, and we put a capacitor here, same way that we did here, there, and we put a VS here, and we put a V0 here. Now to avoid the gain becoming small, we put a bypass capacitor here, CS, C gate, and C drain. So that becomes a common source amplifier. So as usual, you'll do the bias point analysis, which we've already done. Bias point analysis. The goal is to find out what is ID and what is VDS. IDSQ if you want, bias point, quiescent point or bias point, IDSQ, and you want to find out VDSQ. And you want to make sure that VDSQ, before you do your amplifier analysis, you want to make sure that VDSQ is greater than VDSAT. Check. All right, so check that, because to find the bias point, you will use the equation of current in saturation region. So check that it is indeed true. So that will give you the bias point. So that's your first step. Second step, step number 2, you will calculate GM, which will be square root 2 ID beta, and you will calculate R0, which will be equal to 1 over lambda by ID. And in this case, these two, so this is there. So before that, calculate beta. You should know beta. Beta is KPN multiplied by W by L. So whatever W and L are given, find that out. That's equal to beta N. So, right, so you know GM and R0. After that, you draw the small signal circuit. Small signal circuit of this, straightforward. Small signal circuit is you obtain by, if you're doing mid-band analysis. So mid-band analysis, the capacitor would be a short, or if you don't want to put a capacitor as short, you can keep the capacitor here. So keep the capacitor C gate for a moment. R1 and R2 become here. R1 parallel R2. And then there's open circuit. Then there is here GM VGS. This is also ground because this, actually let's do it in mid-band. Let's put this as ground here. VGS here. If you want, you can include R0. You can put RD here and V0 here. And it's very easy to see. Normally R0 would be much larger than RD. Same thing, you will see that the gain V0 by Vs is minus GMRD. Or if you want to be accurate, minus GMRD parallel R0. Same. There it was minus GMRC, here it comes out to be minus GMRD.
So,
yeah.
So if the body and the source are not shorted, how do you calculate GMB?
So GMB is, there's a relationship I've not given you. GMB would be equal to something, say sometimes eta times some GM related to that, all right? There's a relationship. Most of the time we will not deal with it, so that's why it's not given. So GMB is related to GM, okay? So a straightforward substitution replace the transistor by its model, and then you get your. You should also, now what will be the input resistance here? What would be the output resistance here? Output resistance at this point, you can also calculate. Input resistance will be, well, since it's open here, is R1 parallel R2. Output resistance R0 is simply equal to RD. Simply equal to RD. Very similar to what we have done for. Okay. Now this is, so I will not go further with this, but this is what we have talked about is in Nmos. Nmos we've talked about. Now Nmos here, or like this here. We can also talk about PMOS. So PMOS would be, we would represent it like this, arrow coming out, or PMOS we write it like this, many times like this here. Here we show source here at the top and the drain at the bottom and the gate. That's how we normally draw here. Here we draw source, drain, and source and gate. So let me draw the structure of the two so that you can see the differences that are there. This is, we've been saying, there's an N plus here, there is an N plus here, there's an oxide here, and there's a metal here, and this is P type. And this we call as the source, this we call as the source, this we call as the drain source, and we call it the gate and the body. Right? And the normal operation is, in the normal operation we make, let's say, VGS greater than VT, and we apply VDS greater than 0. And the current flows like this here. The current flows from drain to source. Current flows from drain to source. But the electrons, we know, we've already seen the electrons actually flow from here, source to the drain. Actually not at that particular point. They flow at the surface. The electrons flow like this here. They flow from here. They flow like this, right? It makes sense why we call this region source. The electrons start from the source and they go to the drain. The direction of the current is obviously opposite. Okay, so VDS is greater than 0, IDS is greater than 0. Current is entering into this particular node, so this is okay. Let's draw the corresponding complementary structure, which is the PMOS. So PMOS is made on N-type semiconductor, and its source is P plus. This is PMOS, P plus, and it also has a gate, same gate, oxide, and we put on top a metal. So it's an MOS system here, so the same metal here, metal oxide, same here. Okay, and in this case, note that in this case now, this is the gate here, VG, and the body here. So there are some differences here. In this case, what I need to do is create, since it's P plus and this is N, we need to create a layer of holes here, an inversion layer of holes. We need to create an inversion layer of holes here, right? This is the drain, and this is the source here. Inversion layer of holes. So what I need to do is, I typically need to apply VGS, which is less than 0. I have to apply a negative gate voltage with respect to source. Negative, so that there's a negative charge on the gate, balanced by positive charge in the channel. Right? So we normally say VGS has to be less than, here it was VGS has to be greater than VT. We should say VTN. Here we say VGS has to be less than VTP. But VTP is negative. VTP is negative. So for example, VTP could be -1 volt. And so I have to apply a VGS equal to at least minus 1 volt or even lower in order to cause a strong inversion layer. Alright, so these differences are important. Threshold voltage for a PMOS is negative, and VGS you have to apply less than VTP. Then note that what we do is VDS is also negative. We apply VDS negative. VDS we apply 0, less than 0. Why? So if this is ground, we apply VD which is negative. When we apply VD negative, the holes, they start from here and they flow like this. The holes, the direction of the holes and the direction of the current flow is also like this. So according to this picture, IDS is also negative. Note that if I take this current going into a node as positive, then here the current is coming out. IDS is negative. But if IDS is negative, it also implies ISD is positive. ISD is positive. So that's why this symbol here, the current starts from source and then flows to the drain here. ISD is positive. That's why we often draw PMOS with the source at the top and drain at the bottom, because the current is flowing like this. VGS is less than VTP, but the source to gate voltage has to be positive. Gate to source has to be negative, but source to gate voltage has to be negative. Source to gate voltage has to be positive. So this difference we have to keep in mind. The source to voltage, source to drain voltage. So VDS is less than 0, but implies VSD is greater than 0. So if VSD is greater than 0. So if I were to make a MOS amplifier, for example, we saw that we made like this. We made an right ground, and we made like this, right? We biased it here, right? This is drain, this is source, and this is gate. We biased it like this, Nmos. Well, if you want to do it for a PMOS, what would you do? Well, similar, but the difference is in a PMOS, the source is at the top. So you start with source here, and drain is here, and then gate is here. So if you were calling it RD, and you're calling it RS, and you're calling it R1, and you're calling it R2, so we'll put RS here. Note, RS is here, and RD is here. You're calling it VDD. Well, we can put a positive voltage here. We can call it VSS here. And then we can put a voltage divider again. Well, if you want to call the one which is connected to towards the ground R2, well, you could do that. You could call it R2, and you could call this R1. So you would bias it like this. Note that the arrow, the whole thing gets inverted. Here source is at the bottom towards the ground, here source is towards the drain side. Okay? As I said, in all of these cases we are not showing the body, so it's understood that the body is connected to the source here. Here the body is connected to the source here, to this point here. We are not showing it, but body is connected to the source here. Otherwise we have to say what is happening to the body. And the small signal model is exactly same. We have also small signal model of PMOS is same as that. So there is a change in DC, but small signal model is exactly the same. So same gate, same source, same drain, same direction of the current source, everything same. Everything same here. R0 here. If you want to add capacitances here, here, exactly same. Similar, CGS, everything is the same. So, as far as the small signal analysis is concerned, same NMOS model you can substitute there. The terms are the same. The differences is in terms of DC, not in terms of the small signal. Now, so in this case, for example, GM in a PMOS, I would still write square root 2. We would write, instead of beta n, we'll write beta p, and instead of IDS, we'll write ISD, because IDS is negative, so we write ISD. R0, we'll write it as 1 over lambda p, referring to PMOS, and we'll write it as ISD. That's the difference that is there. The current, the DC equations are for this IS, so we write ISD equal to beta p by 2 VSG plus VTP, VSG plus VTP square multiplied by 1 plus lambda VSD. Note that ISD is positive. Current flows from source to drain. ISD is positive. VSG is positive. VTP is negative. VTP for a PMOS is negative. So that's why we put plus here, because it will automatically subtract here, and VSD is positive here. And you need to make sure that VSD is greater than VSD saturation, which is equal to VSG plus VTP. You need to ensure for transistor to work in saturation region, you need to look at this one. So very similar, except for these change in signs that are there. Okay. All right. So with that, what we have done is we know the model of. So let me conclude for the MOSFETs then. For the MOS, what we have seen is basic operation. Basic operation of the MOSFETs, how it works. We have seen a DC model, and we have seen small signal model. Both high frequency as well as low frequency. Right. One of the things that we didn't go, remember when we talk about small signal model, in a BJT, we said, well, base emitter voltage has to be much less than VT for the model to be valid. In this case, well, the small signal gate to source voltage usually has to be much less than, is related to this quantity VGS minus VT. Remember, in a bipolar transistor, it is the base emitter voltage here in this case. Yeah. But in this case, the conditions are not that stringent. You see, in a bipolar transistor, the nonlinearity is very high, e to the power q VB base emitter voltage by kT. Nonlinearity is very high, and to make a linear model, we have to keep base emitter voltage to be very small. While in this case, the characteristics IDS actually goes as VGS square. So the nonlinearity is not very high. So you can apply a fairly large VGS here. Note that VGS minus VT is also large. You could apply VGS equal to 2 volt, VT is equal to 1 volt. So you're talking about VGS, let's say, much less than 1 volt. You could easily apply 100 millivolts. While here, in a bipolar, you can only apply 4 or 5 millivolts. All right, so in this case, the conditions are much more relaxed. You can apply fairly large voltage and still the small signal model would be valid here. All right, so all these things are there now, basic operation, DC model, small signal model. And we just saw briefly that you can take these models, plug it into your common source amplifier, get very similar expressions. You can do common source, common drain, common gate, all of that in a straightforward manner. And the characteristics are also similar here. All right, so let's stop.